Hi everybody, this video is for Thursday, February 8th. We are now in lesson 1.3, so go back to your notes and on page 4 of your notes, you're going to put right here where it says your notes for blank, you're going to write in phase change 1.3. And it starts off by asking our chapter question. It's just a reminder that our chapter question is, what happened to the lake on Titan? Did it evaporate? Did it freeze? So go ahead and take a minute, write down your chapter question. What happened to the lake on Titan? And I'm going to go ahead and continue with the slideshow. You guys will just work your way down from the down in your notes. The next activity was a hands-on activity that we did with the kids, and I'll explain what I want you guys to do with that here in just a second. Okay, so we skipped activity number 1, the bell ringer, the warm-up activity, and we're just going to jump right in. And in the previous lesson, we discussed the appearance of substances at the macro scale during everyday phase changes. So what we see, the appearance of a solid, an ice cube, or yesterday we had an example of a balloon. That's a solid because it holds its shape and does not take the shape of a container. A substance at the macro scale is just looking at what something looks like using only the naked eye. Okay, solids hold their shape and they do not take the shape of their container. Liquids flow and can take the shape of their container, and gases don't have a visible shape and they can fill their container. But just having knowledge about the difference between the phases is not enough for us to solve the mystery of the methane lake on Titan. We need to understand more about what makes the phases different and what actually happens during freezing and evaporation. What's going on at the molecular stage. So we've been talking about macro scale, like I said, substances that can be observed with the human eye, but we have not really started to consider what happens on the molecular scale. And remember, molecules that are too small to be seen with the human eye make it really difficult for us to understand what happens on a molecular scale. But liquid water is made up of 2 hydrogens and 1 oxygen. So again, I'm using the billiard ball model here to help you guys understand that I have 2 different elements, hydrogen and oxygen, that come together in this special bond that make water. We need to kind of think about that. Now, I'm going to remind you, we talked about scale the other day, and unfortunately in your notes, I've got 3 different vocabulary terms here I want to talk to you about. And if you would look at your notes, I don't have any place to put those. So what I would do if I were you is go on to the second page. Nope, not even there. I thought I had more, I had a place for you to take additional notes. If you want to, maybe in with your chapter question, go ahead and write down these definitions, or just at the very top up here, write down the definitions for the hands-on in this hands-on activity. Okay, so scale, remember, is the relative size of things. We're looking at 2 different scales, macro scale and molecular scale. And then we're going to talk about the word molecule. Now, a molecule is a group of atoms joined together in a particular way. When you get into chemistry and you start thinking about how atoms join together, there's lots of words that mean kind of the same thing. So if I'm talking about just one atom, I'm going to say an atom, or I'm going to say an element. If I want to talk about a group of atoms, it could be the same atom, like a group of gold atoms stuck together in the same repeating pattern over and over again. I could call that molecules of gold. If I wanted to talk about table salt is sodium and chlorine. That's not right. Sodium chloride. Sodium and chlorine that are stuck together, one sodium, one chlorine, stuck together the same way over and over again, together make salt, table salt. And so that would be a molecule of table salt or a molecule of water. You might also hear the word compound. That's more than one atom put together in a specific way, too. So, molecule is a group of atoms joined together in a particular way. And then lastly, I've got thermal energy. Now, I know you guys have talked about thermal energy last year. You had a whole big unit on thermal energy. You may remember the term kinetic energy. That's going to come up a little bit later, too. So, here's our definition of thermal energy. Thermal energy is a measure of kinetic energy, which is the movement of molecules. And when we were in class today, when I was talking about this definition, I said, remember kinetic energy, that root word kinetic or K-I-N-E, T-I, it means same thing as a kinesthetic learner. You learn by doing, you learn by doing the thing. You have to have movement, right? So kinetic energy is energy of movement. I put my hands together, and I want you guys to do the same. Put your hands together, but don't move them. So your palms are together, okay? And then if I say kinetic energy is the energy of movement, rub your hands together really, really slowly. And I'm going to do it too, so you might hear my hands moving. So if I'm moving my hands together slowly, thermal energy is the measure of kinetic energy. So if I have increased kinetic energy or decreased kinetic energy, then my thermal energy is going to also increase or decrease. If you rub your hands together pretty slowly, the thermal energy is going to be low because the kinetic energy is low. Now, heat is a measure of thermal energy. So the more thermal energy I have, the warmer the temperature is. The more kinetic energy I have, the more thermal energy I have. So see, it's kind of like one depends on the other. You have to have kinetic energy first. Kinetic energy then will give you thermal energy. Thermal energy will give you heat. Make sense? So if I rub my hands together really, really fast, you do the same thing, your hands are going to get warm. Why? Kinetic energy increased, thermal energy increased, so therefore my heat, temperature increased. And look at what I've got written down there in yellow. If thermal energy increases, kinetic energy increases. And actually, I should say that I need to flip that around. I'm going to see if I can do that. Hang on one second, because that's not right. And I need to make sure that you guys write this down correctly. So it should say if kinetic energy increases, then that means thermal energy will increase. Because remember, we have to have kinetic energy first, and then we have thermal energy. So in other words, if kinetic energy, and notice that I use the abbreviation KE and TE, but I capitalize them. So you can do that too. You don't have to write out thermal energy or kinetic energy. You can just write KE or TE. So in other words, if kinetic energy increases, the atoms or molecules will move faster. If kinetic energy decreases, the atoms or molecules will move slower. That's what I want to say. Okay. I'm going to let you finish writing your definitions and stuff down here, and then go ahead and move on to the next slide. So in class, we had just a really quick hands-on activity in which I had some boiling hot water, and I poured it in a styrofoam cup, and each table got a tray that had a styrofoam cup filled with water, hot boiling water, and then we had a plastic cup that had been kind of cooled a little bit. And what they'll do is, I'm going to show you this video real quick. Over time, I let the kids, I'm going to turn down the sound. You don't need to hear just music. So they've got this boiling water. Now, what they did before they put the cup on is they made some observations. One of the things that they observed is when they just had the boiling water in the styrofoam cup, you could see the steam rising from that. So if you think about a change in phase, it was going from a liquid to a gas. And we can see the steam because that is that in-between state where the liquid is hot enough that it's starting to change into a gas. It's that in between stage. Okay, so they saw liquid turning to a gas. And then I told them to put the clear plastic cup on top. Now that trapped the steam. Okay, so then we have this steam that is collecting along the inside of the plastic cup. And over the course of several minutes, the kids just used their magnifying glasses and they made some observations. They're going to have a close up here pretty quick. Here we go. So, over the course of several minutes, the kids were watching as the steam, the vapor, the water vapor collected on the inside of their cup. And as you can see, the droplets are getting bigger and bigger. And the reason why is because they're starting to collect on the inside and they're starting to get run into each other. And they just get bigger and bigger and bigger. And in a couple cases, I had the kids put ice cubes on top of those plastic cups. And that was just to kind of make sure that those plastic cups remained kind of cool. All right. So in your notes, it's going to be difficult for you because you weren't there. But I had the kids take pictures with their iPads of their experiment and put a couple pictures in the the notes, or I had them go ahead and draw pictures. What did you see? And then I wanted them to label the evidence of the phase change. So again, based just on the video, and you can back this up and take some screenshots and put them in there for you. I want you to take a video and describe the first phase change, which was liquid to gas, and then the gas back to liquid. Make sure that you label what is that change of state called. Okay. If you need help or you have questions about that, you can ask me when you get back, but it's really simple. Just go back and take videos as you're looking through that. Okay. All right. So we just kind of talked about that a little bit here in a discussion. We talked about what changes in phase did the kids observed. And specifically now I want to start asking for evidence. I wanted them to use the words phase and thermal energy in their response. I want you to start thinking about why the phase change occurred. We know if you're looking at like the video that we saw a couple days ago, a popsicle that's going to melt. The reason why it melts is because it's getting warmer. Now think about that. It's getting warmer because the kinetic energy is increasing. Kinetic energy increases, thermal energy increases, temperature increases. So the kids were talking and they were saying at first when they had that boiling water, the kinetic energy or the thermal energy was high. And then when they when they were watching the steam go up, that's what was causing the liquid to evaporate and turn into a gas. And then when they put the plastic cup on top of that and trapped it, the cool air that was surrounding the cup decreased the thermal energy. And so then it made the gas go back to a liquid, which is why we saw that collection of liquid around the cup. Okay, so we've been making observations at the macro scale. Now let's start thinking about what happens at the molecular level. So in your notes, I have this question: what happens to the what happens to the molecules of a substance when it changes phases? What is happening at the molecular scale? Now I'm going to ask you guys to just kind of make a prediction. I want you to use 6 circles to represent 6 water molecules. Only use circles and only use 6. I want you to draw in your notes what you think the water molecules looked like at each phase. So in the first box, we're going to imagine we have ice. You're using 6 circles to represent 6 water molecules. How do those water molecules look in relation to each other? So go ahead and draw 6 water molecule ice cubes. So it's in the shape of an ice cube. Okay? Go ahead and do that. And then what do you think the water molecules look like as liquids? So you're going to draw the same 6 circles, but now as a liquid. And then lastly, how would those 6 water molecules look as water vapor? Go ahead and draw that in the last box. Don't worry about being right yet. This is just kind of one of those times where I ask you to make a prediction, and then we're going to do some investigations in the sim, and then I'm going to give you an opportunity to come back and make revisions on this if you need to. Okay? Okay, let's keep going. So we're going to start activity 3. This is introducing the simulation. Dr. Daniela Flores gave us another email, and she says, you're off to a great start with your investigation of phase changes. Today, you will explore the phase change simulation to further investigate Titan's methane lake mystery at the molecular scale. As you read in the last lesson, Titan and Earth are similar in a few important ways. As molecules behave the same everywhere in the universe, that's a really important thing to remember. Molecules behave the same way in everywhere in the universe. This simulation will help you understand phase change that occurs on Titan. I look forward to your next update. So throughout this unit, we're going to use this phase change simulation to help us learn more about how substances experience phase change on the molecular scale. So I want you just to take a minute to explore the sim and just make some observations. And then after a few minutes, I'm going to show you a video that helps explain the features of the sim. Okay? In order to get there, you are going to go into Amplify. You're going to go into Chapter 1, Lesson 3. And there should be a link in Activity 3. That's where we're at right now, right? Yeah, Activity 3. Why isn't this working? Here we go. Here's Activity 3. We're going to go to Activity 3 and then go ahead and click on that blue link to take you into the phase change. You know, you can also do this. I don't know if you guys are aware. If you go back to your very front page here, if you come up here to those, the waffle icon, that's what I call it because it's all those squares. If you click on that, you can find all the sims, and we are in the phase change sim. So that's this one right here. So either way, both of those will get you into the simulator. All right, so just mess around with this for a minute or two, and then we'll come back and I'll show the video how to actually get started working this. Go ahead and pause this video so you can play. Okay, so let me come back and I'm going to show you the video that goes along with this sim. And as you watch the video, feel free to pause it and try and do the exact same thing in your simulator so that you're able to test out what you see.
This is the phase change sim. You'll use it to learn more about how substances experience phase change on the molecular scale. These spheres represent molecules. Let's press play to run the sim to observe the molecules. On the right are 4 different substances labeled from A to D. Each substance has different attraction levels. You can transfer energy into or out of a substance by pressing the plus or minus buttons under Energy. This is the temperature bar on the left. Press on a molecule to track it. You can also track 2 molecules at once. You can use these buttons to rotate or bump the container. These buttons can change the orientation or movement of the container. You'll use this tool to observe substances on both macro and molecular scales.
All right, hopefully you understand that. We're going to move on. And, I want to identify the phase in each substance is in. So based on what you observe, as we tilt the container, what phase does substance A start with? This is what I mean. I'm going to have you guys go to your phase change. I'm going to click on the play. And each one of these substances is a different phase, solid, liquid, or gas. Okay. I'm going to have you leave the kinetic energy toggle off. We don't care about that right now. I'm going to have you click substance A. You'll notice when you reset this, so I'm going to reset it, it automatically, when you hit play, it will automatically go to the B, but so you'll have to click on substance A. Okay, so here's substance A, and I'm going to rotate substance A, and based on the behavior of the molecules, which phase do you think substance A is? Do you think it's a solid? Do you think it's a liquid? Do you think it's a gas? Well, based on your notes from Wednesday, we said that a solid holds its shape and does not take the shape of its container. And so based on this rotation, if this was not a solid, those molecules would kind of spill over and take the shape of that container. It doesn't. So substance A is a solid. Let me go ahead and reset. I'm going to choose substance B, and let's hit play. And you kind of want to wait a second because those molecules go wacko crazy for a second, and then they kind of calm down a little bit. And so here we are. We're looking at this. And I want to, it can get really confusing. I want to locate two different molecules down here. So go ahead and click on those. And I want you to notice that the molecules are staying pretty close to each other. If I rotate and give it a second, I can see that these molecules are flowing and they do take the shape of their container. They don't fill the container. Notice how I've got some empty space, even though some of those appear to be kind of going back and forth. Most of them stay down below. They take the shape of the container. So substance B is in fact a liquid. Let's go ahead and reset. And we're going to go to substance C and hit play. And here you'll notice that there's no particular shape of the substance, but it does fill the container. So even when I turn it on the side, it's still going to have molecules that go up and kind of bump around, bump off each other. It fills the container. So I'm going to show you. That's a gas. This is a liquid. Watch it. They kind of flow past each other, take the shape of the container. You do have a couple of these random molecules that like to break off and become a gas, but it's kind of interesting because when they come down, they come down. And they're kind of attracted to each other. So once they get close to another one, it knocks them down. And they kind of get pulled down on each other. And then substance B, of course, is a solid. Definitely a solid. Okay, let's come on back. And I want to continue with our simulations. All right, so we identified B and C. And now I want you to work through activity number 4, investigating the molecular scale. So we received, you know how sometimes on different websites they'll have forum questions so people can just ask a question, and then other people who are members of that forum will give an answer. So the Universal Space Agency has a forum, and people are able to post space and science questions. And Titan Fan 5 posted a question and said, I'm trying to determine why the lake on Titan changed phase. But first, I need to know what happens to the molecules of a substance when it changes phase. Can anyone help me understand this? Well, like any good citizens, we've got 3 different people who responded to Titan Lover. What was it? Titan 5? Titan Fan 5. So we have 3 different claims. I Heart Space says, I think that molecules in a substance disappear or no longer exist when a substance changes phase. I think this because when a substance goes from a liquid to a gas, I can no longer see it. Now, claim number 2 from Planet Lover says, I think that molecules in a substance move differently when it changes phase. I think this because when you tilt the container that they're in, a liquid, gas, and a solid do not move in the same way. And then claim number 3 from Science is Cool says, I think that the molecules in a substance change into a new kind of molecule during a phase change. I think this because a liquid looks different from a solid or a gas. So what your job is, I want you to complete this mission. You're going to use the sim to find evidence related to the 3 claims found on the Universal Space Agency's forum. So go ahead and launch the phase change simulation. You're going to cause a substance to change phase. Observe what happens to the molecules of that substance when it changes phase. So for example, go ahead and track 1 or 2 molecules by pressing on them like what I did and make observations. Do whatever you need to do. Tilt the container, bump the container, do whatever you need to do to try to find evidence to prove or disprove those 3 claims. And you can even consider the hands-on investigation that we did as well as the sims. And then you're going to fill out the investigation question section in your notes. So you're going to come back here to your notes, and down here at the bottom of that page, here's that phase change 1.3 activity 4. After following the directions on the screen, which of the 3 claims can be supported? Okay, so you're going to go ahead and fill this in, explaining which one of those 3 claims is correct, and make sure that you use evidence from the sim to support, and I want you to use evidence from the sim to refute the other 2 claims. There's only one that can be right, the other 2 have to be wrong. Make sure that you're using really good evidence to explain which one is correct, which ones are wrong. All right? Okay, that's it for today. Have a good day.